So, last class I have discussed about the pressure meter test and dilatometer test. Now, this class first I will solve one example problem related to dilatometer test, then I will discuss the other in situ test. Now, the first thing that the problem, a dilatometer test was conducted in a clay deposit. The groundwater table was located at a depth of 2 meter below the ground. So, let me draw the figure. So, this is the ground surface and this is the water table. Okay. Now, the water table is at 2 meter below the ground surface and at a depth 6 meter, we have to determine the soil properties. So, that soil property have to determine say this point A and which is say 2 meter below the water, 4 meter below the water. Total is 6 meter depth from the ground surface. Now, here given the P0 is given as 280 kilonewton per meter square and P1 is given 350 kilonewton per meter square. Okay. Poisson ratio of the soil is given 0.45 and saturated unit weight gamma sat is 20 kilonewton per meter cube and gamma bulk which is 18 kilonewton per meter cube. So, that means below the water is gamma sat and above the water is gamma bulk. Okay. Now, unit weight of water is taken as 10 kilonewton per meter cube. So, we have to calculate the K0 OCR E, elastic modulus of the soil. So, you know the K0 expression is for the clay, because this is for the clay. K0 expression is Kd divided by 1.5 to the power 0.47 minus 0.6. OCR expression is 0.5 Kd to the Kd 1.56 and E expression is 1 minus mu square into Ed. Okay. And Kd, because we have to know the Kd and Ed, and Kd expression is P0 minus U0 divided by sigma V bar or sigma V0 bar, effective overburden pressure. Now, sigma V0 bar at Z equal to 6 meter will be equal to, for initial 2 meter it is above the water, that means 2 into bulk unit weight which is 18 plus the 4 into 20 minus 10, because here we have to take the submerged unit weight below the water table and this is the submerged unit weight, or sometime it is called gamma dash, which is gamma sat minus gamma W. So, above the water table is gamma bulk and below the water table gamma sub or gamma dash you have to use. Sometimes in the problem you may find that above the water table and the saturated unit weight below the water table are same. So, you have to use according to that. So, this is 10. So, this value is coming out to be 76 kilonewton per meter square. Okay. And the U0 pore water pressure at 0.6 will be 4 into 10. So, that is 40 kilonewton per meter square. Okay. So, now if I put this value here, that P 0 is 280 minus U 0 is 40 divided by 76. So, this value is 3.16. So, KD value is 3.16. Okay. So, KD value will get 3.16. Similarly, we will get the ED value also. So, ED value is equal to 34.7 P1 minus P0. So, that is equal to 34.7, P1 is 350 and P0 is 280. So, that is equal to 2429 kilonewton per meter square. So, we will get the KD and the ED. Now, we will determine these properties K0, OCR, E. So, K0 will be equal to KD is 3.16, this is 1.5 to the power 0.47 minus 0.6. So, that is equal to 0.82. Okay. And OCR is equal to 0.5 into KD, that is 3.16 to the power 1.56. So, that is equal to 2. So, OCR is 2 and elastic modulus E, which is 1 minus 0.45 square into ED, which is 2429. So, that will be 1937 kilonewton per meter square. So, this way we can determine the required properties if I know the P0, U0, P1. Okay. So, by use an effective overburden pressure. So, we will get the required properties for the soil. So, and this way we can determine the other properties also that I have discussed in my previous lecture. So, now I will go for the next test, which is called the Vane shear test. So, this Vane shear test is suitable for very soft clay. Okay. So, this field Vane shear where we basically apply a torque. Okay. So, we apply a torque and then we measure this torque required to quickly shear the vein pushed into the ground surface or into the soil. So, that means that we measure the torque required to quickly shear the vein pushed into the soil. That means, the vein which is pushed into the soil, we have to apply the torque and we measure the torque that required to quickly shear that soil. Okay. So, typical diameter of the vein is 20 to 100 millimeter and the height of the vein. So, this is the vein, these veins heights are generally 2 times of diameter. Okay. Height of the vein is 2 times of diameter of the vein. So, once we apply this torque and then we measure these torques, and if we know the diameter and height of the vein, then by using this correlation we can determine the undrained cohesion of the soil, and it is basically applicable for soft soil. So, undrained cohesion of the soil, this is the torque applied, height of the vein and diameter of the soil cylinder shear. Okay, so diameter of the soil cylinder means basically diameter of this vein. So this is the, or diameter means this total hole diameter. So that means this is the one blade and this is the another blade. So these two blades, that means the total hole diameter is equal to d. Clear? And that h is 2 times of that t. So that's why it is written the diameter of the soil cylinder. So this way we can determine the undrained cohesion of the clay. So now next part, so these are the tests that I have discussed, in situ test by which I can determine the soil sample, few are directly and few are indirectly. Now the next part, and I have discussed that in several times, that if we require to collect the soil sample, then we have to use the sampler tube. Now the question is how we have to collect the soil sample. Okay. Now, what are the different types of soil samples? So here the two types of soil samples are there, one is disturbed, one is undisturbed. So what is the definition of disturbed soil sample? The disturbed soil sample is that in which the natural structure of the soil gets modified either partly or fully during the sampling. And the undisturbed is that means the natural structure of the soil will not be disturbed during the sampling. So the undisturbed soil sample, where the natural structure of the soil will not disturb, and in the disturbed sample the natural structure of the sample will be partly or fully disturbed during the sampling. Now again I have discussed that we have to use the disturbed soil samples also. Now where we can use the disturbed sample? The disturbed but the representative soil sample can be used for grain size analysis, for determination of liquid and plastic limit, specific gravity of the soil, organic content determination and soil classification, because in these cases whether soil is disturbed or undisturbed, it will not matter. But the undisturbed soil sample must be used for the consolidation test, for hydraulic conductivity test and shear strength test. That means the track shear or the direct shear or UCS. So where we have to use the undisturbed soil sample, because these data are required for design the foundation. That means for two bearing capacity calculation and settlement calculation and permeability. I mean hydraulic conductivity test or the permeability is also important parameters, because your consolidation depends on the permeability of the soil. So that means the permeability, consolidation parameter and the strength parameters. So these parameters you have to determine by using the undisturbed soil samples. Okay. So now the next one, so how we can collect the undisturbed soil sample? What are the criteria? So for the track shell or the consolidation test in the lab, we have to collect the undisturbed samples. So criteria that the area ratio of the sampler tube should be less than 10%. Now what is area ratio? So it is expected that if the thickness of the sampler tube is more, then disturbance will also be more. So that in the sampler tube's thickness will influence the disturbance. So that means we have to make the sampler tube thickness as small as possible to reduce the disturbance. So now if and the sampler tube is the hollow tube, okay, so that sampler tube have the has the inside and outside diameter. So if this is the area ratio, outside diameter square minus inside diameter square divided by inside diameter square, it is expressed in percentage. If it is less than 10%, then the soil sample that I will collect, that will be disturbance free. And we have to be very careful during the transportation of the sample also. Only the collection is not sufficient. We have to transport it, the soil sample, from the site to the lab. So that time also you have to be very careful. Our IS code also recommends few others criterias. So this is our sampler tube, and in the sampler tube, there is a cutting edge is attached at the front of the sampler tube. So, that means if the sampler tube inside diameter is D3 and tube outside diameter is D4 and the cutting edge inside diameter is D1 and outside diameter is D2, then I can get these values also. Ci is the inside clearance, and these I can get by using these expressions Ci, then I can get the C0, I can get the area ratio also. Now, according to IS code, for a good recovery, the Ci should be in between 1% to 3%. C0 should be in between 0 to 2%. Area ratio should not be greater than 20% for stiff formation, and for soft sensitive clay it should be less than equal to 10%. Then by measuring the length of the soil sample also we can understand whether the sample is disturbed or undisturbed. How we can identify that? So, we can identify by recovery ratio. So, this recovery ratio is equal to LR, which is the actual length recovered sample and theoretical length recovered sample. That means, if your actual length within a sampler tube is less than the length of the tube, then what will happen? It indicates that the soil has been compressed, and if your actual length is equal to the theoretical length of the sample, then the soil is intact, and if it is actual length is more, then soil is been expand. So, that means that is why if LR is 1, that means the LR indicates that good recovery, and less than 1 indicates that soil has been compressed. That means your actual length, recover length is less than the theoretical recover length, and if LR greater than 1 indicates the soil has been swelled. So, that means the actual recover length is greater than theoretical recover length. Then type of samplers. So, that means there are two types of sampler, one is thick wall samplers, another is thin wall samplers. Thick wall sampler is called split spoon samplers and thin wall sampler is called cell by tube. And split spoon samplers, so this is the description of the split spoon samplers. So, there is a cutting edge is there in the front of the sampler tube, and a sampler split spoon sampler inside diameter is 35 millimeter or 34.3 millimeter, and external diameter is 50.8 millimeter. Okay? And then the sample is generally taken in interval 1.5 meter or 5 foot, and this sampler tube it has two halves, and this is the sampler tube which has two halves. Okay, and this is the sample inside these two halves, and these sampler tubes are pushed into the soil by hammer blow, and the soil is collected from the site. So, these are the two couplings which are unscrewed during collection of the soil sample after taking from the site. So, this is the samples, and as I mentioned, the inside diameter is 35 millimeter and outside is roughly 50 millimeter, 50.8 millimeter. So, the area ratio will be 50.8 square minus 34.9 square divided by 34.9 square into 100, 112%. So, that means the samples that we are collecting by using split spoon sampler, then those samples are highly disturbed samples. Now, for thin oil samplers or the cell by tubes, where the outside diameter is 50.8 and inside or 76.2 types, one is 50.8 millimeter, another is 76.3 millimeter, and the inside diameter of the tube is 40 47.663 millimeter, whose outside diameter is 50.8. So, the area ratio is 13.75%, which is close to the 10% which is the requirement. So, that means if I use the thin walled sampler tube, then the sample that I will get that are disturbance free. That means it is a good sample or the undisturbed sample I can collect. So, this is a particular sampler cell by tube or the thin walled sampler tube. This is the tube which is pushed into the soil to collect the soil sample. Now, how many boreholes we have to construct during the soil exploration. So, that depends on the type and the size of the project, the budget of the site investigation and soil variability, which is very important. If we have the huge, we have the variation of the soils between two boreholes, then we have to definitely take more boreholes between these two boreholes. So, this is the some guidelines. Then the spacing of boreholes, that depends on the type of the projects also. This is some guidelines are given. So, that means a multi-storied building 10 to 30 meter, one story by industrial plants 20 to 60 meter, highways 250 to 500 meters, residential subdivision 250 to 500, dams and dikes 40 to 80 meter. This is the spacing between boreholes. Then based on the number of stories also, borehole depth can be determined. For one story building 3.5 meter, for 2 story 6 meters, similar to 5 story 24 meters and so on. For a building with width of 30.5 meter. Now, in general case for the fallow foundation, as we know that for the shallow foundation bearing capacity purpose, determination purpose, we go for up to width of the footing, and for the settlement calculation purpose we can go up to 1.5 to 2 times the width of the footing. So, for shallow foundation we can go up to say 2 times from the base of the footing as my borehole depth. So, up to which we have to collect the soil sample. So, next one is the groundwater table location. So, that the correct indication of the groundwater table is found by allowing the water in the boring to reach equilibrium level. So, that means we have to construct a borehole and then we see whether the water level is reaching equilibrium at what level. Okay. So, that means if the soil is sandy soil, then the water level which quickly stabilize. So, we can within few hours, so we can identify the water level. So, that means we construct a borehole, put the water into the borehole, and then that water will quickly reach or quickly stabilized and will reach the groundwater table level. So, for sandy soil it will reach very quickly, and we can within a few hours we can identify the location of the water table for sandy soil, but for the clay soil it will take several days to reach that equilibrium or the stabilization. So, for that purpose, for clay soil that we have to use the standpipes or the piezometers to identify the water table. So, for the sandy soil we can by borehole we can identify the water table very quickly, but for the clay soil we have to use the piezometers. So, what is the methodology by which we can identify the water table for clay soil? So, this is the observation of water table by piezometer, and this is for the clay soil where the water table or the if we put the water into the borehole it will not stabilize very quickly. Suppose this is the your standpipes or piezometer is inserted into the borehole, and then we measured the water level at different time interval. So, this is your borehole and we put the piezometer or the standpipe into the soil, and then we measure the position of the water of this borehole at certain time interval. First, we have to remove the water from this borehole, then this water will come into the equilibrium condition. So, it will take time. Okay. So, water to come into the equilibrium condition. So, it will come very slow intervals, it will take days and it will come in very slow rate. But that change in water level we can measure by piezometer, and then by using expressions we can determine what would be the location of the groundwater table. So, that what is the location? Suppose initially I do not know what is the location of the groundwater table, but I know the position of the water level at t equal to 0 time. So, that height, that means the H0 plus Hw. Hw is the height of the water table from the ground, but initially I do not know, but I know Hw plus H0 initially, because that is the water position at the borehole at t equal to 0. Now, at t equal to T1, then the position will be at this level. So, I can measure the what is the rise of the water table. So, that will be del H1. At t equal to T2, again further rise will be there, that will be del H2, and t is equal to T3, then will be further rise of the water table, that will be del H3. So, that del H1, del H2, del H3 I know, I can measure. So, once I get these values, so I will use these equation. So, from here I will calculate is your H0 del H1 square divided by del H1 minus del H2. Okay. And I will get H2 is equal to del H2 square divided by del H1 minus del H2, and H3 is equal to del H3 square divided by del H2 minus del H3. Okay. So, ideally all these values, that means the H0, H2, H3, that means their end point will be on a particular line. Understand what I am saying? That means here if I know the H0, as I mentioned, that I can identify this position of the water level at t equal to 0 from the ground, that is possible. Now, if I know the H0, I can subtract this value from this total height, I can identify the groundwater table. But this additional H2 and H3 will help me to get this data, because that will also confirm you that this is the position of the water table. Okay, because that H2 also from the water table, H3 also from the water table. So, that these things I will discuss by a example problem in the next class, that how I can measure this data and then how I can use this data to identify water table. So, next class I will first solve one example problems on related to observation of water table by piezometer for clay soil. Then I will go for the next type of soil exploration, that is geophysical exploration. Thank you.